Go. So we're going to do section 11.6 and discuss some of the properties there. Properties of logs. I kind of got distracted for a second because my dog just came and sat down at my feet here. So he's kind of comfortable like yours, Courtney. In any case, these are the properties of logs that you should know. Now I've crossed out this bottom one because I don't think I'll ever give you a problem that would require that. But I did add a little bit to this, to the basic properties of logs that you're going to have. So the first one I would call your product rule, then your quotient rule, then your power rule. The one that I have the blue arrow to, that's the change of base formula. So if you were stuck calculating log of some base that you didn't know, you could use that. But nowadays, that kind of thing is built into your calculator, depending on which one you're using. Now, if you're using a TI-84, you can find it from the math menu. Then I think scrolling up is a little bit faster to get the log base whatever. It allows you to do, for instance, log base 6 of 1296 should work out nice and even. 96, bam, 4. If you're doing it on Desmos, again, you can do it. I think you want to go over to function. And then, let's see. You know, I'm not seeing it here at the moment. I thought there was a place to do, we found it at one point. So, well, at the very least, what you could do is use that change the base formula. And the change of base formula for log base 6 of 1296 would look like this. It'd be log of 1296 divided by log of 6. That's what the change of base formula would say. So let's take a look at that on Desmos real quick. So it'd be log of 1296, then exit the parenthesis or put in a parenthesis, divided by log of 6. And there you go, 4. So nailed it. But mostly what you're going to be doing in section 11.6 is playing around with the rules for logarithms. So let's start with this example, example A, kind of something you could see in WebAssign, log of RS, or excuse me, R over S times T. Now they've kind of set it up for you so that you don't have to enter too much. So it would look like this. First thing you're going to use is the quotient rule. So it's going to be log of R minus log of S and T. And that's the first thing you're going to put in here is that S and T, because that's the denominator. So you're just using your properties of logs. In this case, you'll be using your quotient rule first. That's our first things. From there, we can continue to simplify this. It's going to be log of R minus, and I always do this for my face-to-face classes, log of S plus log of T. So just log of those. I'm using the product rule here, but there's actually a mistake that I've made. Can anyone see what that mistake is? Where did I go wrong?
Would it be that negative sign and then the plus sign right there in front of the log T?
Yeah, so here's what happens. When you expand this, it looks like this. But notice that if I put parentheses here and expand it here, that's all fine. But initially when I wrote it without parentheses, the sign on this term would be wrong. You've got to distribute that negative to both terms. So just as you were saying, and thank you, if I didn't have that parenthesis there, then the sign on this would be wrong. It should be log of S minus log of T. And you don't necessarily need to put parentheses around just one term here, but yeah, I don't know. I did. So that's what you'd have to fill in the rest of the way. And let's take a look back there. So there you go. So I think this last little piece here is just a matter of filling in the sign. Would be all you have to do. And then here you have to fill in a t. Okay, so that's a little bit of practice with your quotient rule and your product rule. Let's practice a couple more with some more advanced rules. Now, one of the things I tried to get across in these videos is that the logarithm and the exponential functions are inverses of each other. And we've seen inverses before. When we had an inverse back earlier in section like 11.1, we had something like this. F of f inverse of x was x. And then we'd have f inverse of f of x was also x. Basically, if we do a function and then its inverse, they cancel each other out. Like the cube root of y cubed gives me y. Those are inverse operations. The same thing is true with logarithms. When you're dealing with logarithms and exponential functions, those are inverse operations. And there's two properties that reflect that. This one right here, and this one right here. That is, when you have a to the log base a of x, that's just going to give you x. Or the other way around that you could do a function and its inverse is log base a of a to the r gives you r. Both of those are showing you the same kind of thing that I see here, or the same thing I see here. The function and its inverse cancel each other out. Now, to practice that a little bit, let's start with this example. And let's remind ourselves what the logarithm is saying. Now, would happen that I didn't write a very crisp looking one here. There we go. So it's 10 to the log base 10 of 1,000. Now we'll do this a couple ways. And what I hope is that eventually you're going to get the fast way. Let's just think about the exponent. This part right here. And in particular, remind ourselves what the logarithm means. The logarithm is telling you what power of 10 would give me 1,000. So what would that be? What power of 10, 10 to the what gives me 1,000?
3.
3, excellent. So I can replace this whole thing with 10, or this whole thing with 3, and that leaves me with 10 to the third power. What's 10 to the third power?
1,000.
1,000. Oh. No, you're right. That's it. 1,000. And you're done. The thing that I want to point out, though, is that there's kind of a shortcut. Right there. When this base and this base are the same, then you're just going to get whatever number there is there. Always. So let's see a couple more problems like that. For instance, 6 to the log base 6 of 8. What would that equal?
8.
8, yeah. So notice that this 6 is kind of like a subscript. It's not written on the same line as the log and the 8. It's a little bit below. So that's your base. So 6 to the log base 6 of 8 is 8. How about another one like that? 5 to the log base 5 of 87.
$87, I guess.
Yeah, 87. So the nice thing is that these things cancel each other out because you're doing a function and then it's inverse. Let's think about it this way. log base 5 of 87 is saying, all right, the number I get when I calculate this is the number that I raise 5 to get 87. So it's some number, whatever it is. I raise 5 to that number and I get 87. Well, if I then do 5 to that power, it should give me exactly 87. And it does. Now, here's what I want. I want you to write a problem like that for yourself. Write a problem like one of these three. So A, B, and C. Write a problem for yourself just like that, and then solve it. So do this part and then solve it. Can someone share with me an example that they got? Someone I haven't heard from yet this morning.
So one could be 10 log base 10 of 50, or like with the exponent 50.
50?
And that would equal 50.
Yep. Perfect. And that one's a nice and friendly one. So let me show you here what that is. Now the log base 10 of 50, this is a great example. I appreciate you saying something. So log base 10 of 50. Now I don't have to write the 10 there because it's understood. So it's just log of 50. And what that means, or what this number represents, is 10 to this power should give me 50. In fact, I can check that. 10 raised to this power. Now you can do it like this. Just press enter to get that in there. I'm going to hit the answer key, second, and then that minus. That gives me the exact full precision of this number. 10 to this power should give me 50, and it does. That's perfect. Perfect. I like that one. There's another way that you can write this relationship. It's not just, a base to this power, of log, base, whatever. You can write that in a different way, or you can see that property, those inverse properties in a different way, and that would be this one right here. Log base A of A to the R. So let me show you an example or two like that. So it'll be log base 3 of 3 to the 9th power. Now there's a couple ways you can solve this. And one way I'm going to solve this is by practicing your rules for logarithms. So the one way I'll solve it is by first using the power rule. The power rule says I can take this exponent out in front, and that'll give me 9 times a log base 3 of 3. Now log base 3 of 3, well, that's something that I think I can simplify without a calculator. Because basically you're asking yourself, what power of 3 to what power gives me 3? 3 to the what gives me 3? First, yeah. And in fact, if you look back at the handout that I gave you on the different properties of logs, one of the properties that you can use is this one right here. Log base A of A is 1. What power of A gives you A? Oh, first power. If these things match, it simplifies to a 1. And 9 times 1 is 9. Beautiful, beautiful. But there's a shortcut here. When these things match, When those match, you just get the exponent. So for future problems, maybe you can just jump here to the happy ending and get a 9. For instance, log base 4 of 4 to the 8th power. What's the happy ending on that one? Anyone?
8.
Got to vote for 8. Does anyone else agree with Lynn?
Yeah.
Yes.
Yeah. Again, these things match. So it's a function and it's inverse. And they cancel each other out, you get 8. Beautiful. Now, let me do one more from this section that involves your properties of logs. And it's just some review of your quotient rule and your power rule. So I could have, for instance, log of, say, the cube root of x over y to the 5th. I can't remember if I joked with people in my video or not about this, but you would start out with log of the cube root of x minus log of the cube root, or log of y to the 5th. And the joke was, oh, did I forget to give you the property of logarithms and radicals? And then it'd be, oh, well, that's because there isn't one. Instead, what you have to do here is you have to rewrite this using exponents. So instead of the cube root of x, what can I write there?
X to the 1/3.
Excellent. So if you just put a 1 in here as kind of a reminder to yourself, you could use what we did earlier in the semester. I called it the reverse boot method, but it's x to the 1/3 power. And thank you to whoever got that. Y to the 5th. And there's one last little thing we need to do here, but definitely rewriting the radical using exponents allows you to finish this problem. What's the last property of logs that I'm going to use here?
The power property.
Yeah, thank you, Grace. So our power rule allows us to take those out in front. So I'll end up with 1/3 log of x minus 5 times the log of y. Beautiful, beautiful. How are we looking there?
Cool.
Doing good?
Yep.
Okay. So that's all section 11.6, which I've kind of covered out of order because the properties in 11.6 actually help you out with stuff in section 11.5. So let me work backwards and do section 11.5. So a couple of properties here will be stuff like this. ln of e cubed. Now the thing that I hope you got the most out of the videos that you watched for this was that ln is really log of what base?
E.
E. Perfect. So it's log base e of e cubed. Now, you could solve things from here, but I think hopefully here it's a little bit clearer to see how this is going to simplify. How does log base e of e cubed simplify?
3.
Yeah, 3. Because again, these match. So it's just equal to 3. So it's your inverse property of logarithms and exponents again coming in. Log base 3 of, or log base e of e cubed is just 3. You can actually do that one on your calculator if you really wanted to, you know, feel comfortable. You can do ln of e to the 3rd power Oh, and 3. But it's a pain. It's a pain to try and type that in. So it's better just to be able to realize that. Let's do a couple more like this. I'll start with ln of the square root of e. And maybe after the example I did 2 examples back, maybe you can tell me what to do here.
Is it e to the 1/2 power? Log base
Nice. So that becomes square root of e becomes e to the 1/2 power. Perfect. Someone else want to help me finish this one? How does that one finish up?
Wouldn't it just be 1/2?
Yes, perfect. 1/2. That's it. Again, these match. These match, then these are inverse functions. So, yeah, get you back to where you started from. Okay. We're going to do one more like that, and then I'll finish up with a compound interest problem. But the last one I want to do like this, and maybe I'll do it in a couple different ways. Let's see here. ln of, no, sorry. I'm messing that up. ln of 1 over e squared. Now there's a couple ways we can do this one. I guess the first thing that I'll note for you is that we can use our quotient rule. So it'd be the ln of 1 minus the ln of e squared. Okay. Now, ln, at least in my experience, ln is just a little bit too abstract. So what I can do instead of writing ln is write log what base here? Anyone?
e.
Excellent. Log base e. And now both of these are going to simplify pretty nicely. Somebody for log base e of 1. And if you want to look back at some of your formulas or properties, go ahead. That was over here, properties. Yeah, I see a particular property. Yeah, exactly. 0. Log base a of 1, anything. Doesn't matter what the base is, as long as it's a legitimate base. That's a big fat 0. Excellent. Someone else for this one. How does this one simplify?
2.
Nice. Again, those match. So this just gives me a 2. So I end up with 0 minus 2, which is negative 2. Beautiful. Beautiful. Now there's another way that I could have done this one, and that is, let's see, instead of writing it as ln of 1 over e squared, how about if I write it as ln of e to some power? Except what would that power be? Can anyone tell me?
-2.
Nice, nice. Well done. That'd be ln of e to the -2, which is log base e of e to the -2. And now I can finish evaluating this. What would that equal?
-2, the e's cancel.
Yeah, thanks, Courtney. -2. Nice. So either way, you get to the same spot. And now it's up to you what you feel comfortable with. I mean, certainly I like that one, but both of them work. And it was a good review to do it both ways. Comments on that one before I do an interest problem? Now for your compound interest problems, you had stuff like this. A P, R, T, P. E, of course, is the base of your natural log. A is typically unknown. P is your principal. R is your rate as a decimal, and T is time. Your Web of Science seems to be a little bit fond of using negative values for the interest rate, which I find kind of strange. But you can think of it this way. You can think of it as a depreciating asset. Maybe you buy something and it just wears out over time. And they're going to amortize things over 27 years, which probably going to get more than a 2% decrease in assets. But whatever.
Would that model inflation?
Yeah, maybe it's eating away the value because of inflation. Yeah, that's not too bad. Inflation's been pretty low the last couple of years. So, all right, let me copy down a few things here. So it'd be 33,992 is the principal. Negative 2% is the interest rate. Of course, you got to write that as a decimal. So we'll take care of that in a second. And then 27 years. So let me flip back over to what I'm writing in case you're trying to follow along here. Let's plug in all this information. 33992 e to the negative, what's 2% as a decimal?
0.02.
0.02. You've got to put that in as a decimal. And then R times T, that's 27. Great. Now I'm going to put this into the decimals calculator, do things there. I had somebody in my morning class trying to use the percent stuff. Now let me see, let me go back to the main here. Yeah, there's some percent stuff, which I don't know how that's used. So I'm just going to stay away from that. We'll see if we can't calculate this one. It's going to be 33,992. And then E, you're going to hit the raise to key, and you got to put parentheses around this. It seems that if you don't, then decimal is going to just put the next thing that you write, down back on the same line again. This is an exponent. So it's going to be negative 0.02 times 27. And there you go. 19,808. Now you're going to have to round that to the nearest penny, I'm guessing. So to the nearest hundredth, what would that round to? So the nearest hundredth, that would round to, 0.78. If you're doing it on a graphing calculator, let me give you a quick view on that as well. So let me clear out the stuff here. $33,992. Then I hit the second ln key. That gets me to e to the x. You could do e here, but then you'd have to also hit the shift key there. I just do it this way. Negative 0.02 times 27. That should give you exactly the same thing. And I do. Nice.
I have a quick question, please.
Yeah, Z.
This negative the negative percentages, that's reflective of depreciation. Did I hear that or no?
No, this is exactly right. And if you take a look at the graphs on, say, Desmos, and let me just open up a quick Desmos page here for you. Let's see, graph. I can do y equals e raised to the 0.09x. So that's an increasing function. So you can see that as you move out further and further over time, that it's increasing. But if I had the same thing except in a negative exponent here, then what's going to happen is that's going to be a decreasing function. So that over time, you know, the value is going to be decreasing. You can see the blue line is getting smaller and smaller over time, where the exponential line over here is getting bigger and bigger. So what people are worried about with the coronavirus, for instance, is this exponential growth. Right now, the positivity rate in Michigan was like 9%. And you've seen a huge spike, exponential growth in the number of cases. I mean, the last I saw, we were up around 4,000 cases a day. And like a month ago, we were around 1,000 cases a day. So it's growing exponentially. So does that help? See?
Yes, thank you.
Okay, cool. Any other comments or thoughts here? All right, let me stop the video here and put you in your breakout rooms.